One of the operations that I don't see here explained is the post selection, the post selectors. And but I found a blog post where this is explained, I think, and I wanted to go through that today. Let me show you quickly. So we've got post select off, post select on, and then we've got also post select on the x-axis off or the x-axis on, etc. Right? So and I want to kind of understand a bit what's that, because these basically pause select 0, pause select 1 omits 100%, and the notation here of the cat and the bra, it seems like so. But luckily enough, look this. Pause selection is cheating. Recently, two demonstrations of calculation were published in Nature with independent sources and practical solution much further network by Valivarti. I want to talk about the difference between the two. In the Valivarti paper, they describe the last step of the teleportation like this: operates pairs of photons in the maximally time-being entangled state, sends the photons to Charlie, where they are projected jointly with the photons from Alice into the maximally entangled state. Whereas here's how Ki Chao San describes the teleportation process. The paper. Charlie sends the idler photon to Bob and holds the signal photon by propagating it in a 15-kilometer coiled optical fiber. Bob holds the idler photon. Similarly, after he receives the temporary storages allow us to perform the Bell state measurement after entanglement distribution and implement the feed-forward operation in real time. I haven't understood a word of this. No projecting, but about performing operations. Let me make the difference more concrete by focusing on some quantum circuits that are analogous to the two papers' respective protocols. Here's a circuit animation corresponding to a simplification of the Ki-Chao-San et al. Implemented. Mm-hmm. Mm. It's kind of, that's more the traditional one where, or the one that I've seen, like where those operations are conditioned on the measurements of those. As you can see in the animation, the circuit moves the top qubit state to the bottom qubit as you go from left to right. The circuit creates a pre-shared EPR pair, uses an arbitrary gate to choose a qubit for Alice to send, does a Bell basis measurement for Alice, and then tells Bob the measurement result and applies some conditional fixed amp operations. It's a typical quantum operation example. It's a typical quantum operation circuit. Now here's a circuit responding to a simplification of what the Valivarti et al. Did. Okay, so in here we've got post selection. Okay. Interesting, because there's no operations. The state still moves from top to bottom, but without Bob applying any fix-up operations. Instead, any runs where those fix-up operations would have been applied are discarded, and we focus on analysis of what's left. Putting it bluntly and really unfairly, Ki-Chao-San performed quantum teleportation. Valivarti skipped the hardest part of teleportation, cherry-picked the 25% of runs that weren't ruined as a result, and showed that if they hadn't skipped the hard part, they would have performed quantum teleportation. I mean, Valivarti et al. Didn't even have Bob hold his qubit long enough for Alice to do her measurement. We point out that the 795 nanometer photons are measured prior to the Bell state measurement, thus realizing a scenario where teleportation is achieved a posteriori. So it would be more accurate to describe the experiment as Bob predicting things about Alice's measurement result, not Alice heralding whether Bob received the cube or not. Don't get me started on people who somehow forget about the cherry picking and then say the information actually went into the past. There are in some contexts where you can retry until the process works, your protocol would work fine. For example, one of the recent loophole-free Bell inequality experiments. It's just that, to me, leaving off the hardest part of quantum teleportation, but still calling it quantum teleportation without any qualifiers feels like cheating. So I strongly prefer Ki-Chan Sandal's paper. So this past selection, it's just kind of ignoring the results. So it's almost like a measurement, but without actually measuring. Or I mean, it's literally. So this is literally keep the on states and discards the other ones. So if you do this and you do that, here it means 50%. Okay, so we've got like 100% of measuring 0, 1. Kept 50%. Okay. But I don't know, in what cases is this helpful? Is it, are you actually measuring? Can I do here? I don't know. Can I do a Hadamard afterwards? Yeah. Whereas if I measure, should be able to do a Hadamard. No remix. Sorry. So I can't do a Hadamard here because I've measured, so I've collapsed. So this is almost like saying filter. It can still work with those qubits. Post selection. So showing here post selection. So there's something else. Erasure is post selection. So there's only 2 mentions. What's actually happening? Okay. This erasure is possible. For a few months, I've intended to revisit my quantum mistakes. Was committed in the past, and there was some back and forth, but we still disagree over whether his algorithm works. I'm the one who thinks it obviously doesn't. One of the mistakes Walters makes is actually a widespread misconception, so I figured out I should talk about it separately. Thus this post. Lay erasure. Here's a typical lay summary of a quantum erasure experiment. Even though we've done nothing directly to the signal photons by erasing the which path information carried by their idler partners, we can recover an interference pattern from the signal photons. This explanation isn't wrong because Brian has something very specific in mind when he says can recover, but it's seriously misleading. Even worse, it's misleading in a way that most explanations of erasure experiments are. Specifically, if I bet most readers end up thinking that interference pattern simply reappears as if the elapsed photon had never existed. Don't believe me? Or that is a misconception. I started in the quantum rays demystified. It's well done, assuming you understand code. If only I didn't fall prey to the misconception I'm complaining about. Misconceptions are just lay audiences. I either don't want to single him out, but then there's this paragraph from his paper measuring the projection. Measuring the projection of the scratch bead along the z-axis would resolve which branch of the conditional statement was executed and destroy the probability for states which correspond to the other branch. Instead, this information is deliberately destroyed by non-selectively measuring the scratch bead along the x-axis. Clearly, a lot of people think that measuring one qubit can directly affect another. So what's actually going on? What's actually happening? People think that the quantum eraser works like the following circuit, where an operation on one qubit affects the state of another. But actually, in the depicted situation, the other qubit is always unaffected. You can never observably affect one qubit by operating on another. It doesn't matter how complicated you make things. Doing so is a trivial violation of the non-communication theorem. Actual eraser experiments get around the non-communication problem by conditioning. However, we often think of this conditioning in terms of post-selection. We throw out all the runs that don't meet some criteria and look at the remaining ones. So it's a conditioned measurement. It's a conditional measurement. Is it? So you're post-selecting the ones. So you're now left with zeros up here. Okay, note that the last circuit looks like a lot like the misconceived circuit I started with, but they mean very different things in practice. Measurement doesn't require coordination, but post-selection does. If Alice has the top qubit and Bob has the bottom qubit, Bob has to tell Alice which runs she needs to throw out. Surprisingly, describing experiments in words has the same post-selection. Sounds like measurement issue that the circuit diagrams do. It can be hard to spot the distinction. For example, consider the quantum rays experiment that starts with a two-slit experiment that covers one slit with a horizontal polarizing filter and the other with a vertical polarizing filter. The idea is that each photon's polarization contains the which way information, and by placing the photons end up diagonally polarized, thus erasing the which way information the occurs post-selection. The diagonal polarizing filter throws away half of the photons. If you looked at the missing half, you'd find it contained an exactly complementary interference pattern, but the two together, put the two together, do the measurement but not the post-selection, and the result is no apparent interference pattern. Consequences. Erasing an entangled qubit's value requires an interaction between that qubit and its entangled partners. For all For all intents and purposes, post-selection counts as an interaction. It's easy to confuse measurement and post-selection, especially when grouping results or using polarizing filters. Be careful. Okay, so basically, basically the difference is past selecting is like a measurement where you discard parts of your measurement. That's basically what this is saying. So in this case, you would try to reproduce what? Okay. So in this case, if I measure this qubit, and now I condition a measurement. Only if I see a 1, then I will measure this one. Control, sorry. No? You can control measurement. Okay. Yeah, so we see it's a 1. Basically. Which is what happens if we're doing a past selection. We're saying measure and discard the zeros. So what this does is it affects the rest of the qubits. But it's not to say, and it's smart that there's this dotted line here. It's not to say that this action is only happening in this wire and it affects these other ones. Is that if you're measuring, okay, I mean, it is simply, it's basically simply a, yeah, it keeps the on states, discards the other ones. Curious if I would now say, and I'll do a past selection on this. Okay, interesting. What's this? Past selection on this. I mean, it's 50%. So basically removes the entanglement. Does it? Yeah. It doesn't matter where you put the past selection, you past selecting. You're saying keep only the on plus off states. Interesting. You say keep only the 0 states, or keep only the 1 states, keep only the minus states. Can even do this, keep only these states. Yeah. Okay. But this is not performing a measurement, right? Because it helps me transform 0 into this. Oops. Discards 1, discards 0. So I can still do that. else if I measure this? Basically. So it's basically the saying is like you're not. This is kind of cheating in the sense that you're not doing it in a way that is generic enough because you're not guaranteeing that that what's happening on the other with the other states, with the states that you're trashing, that this actually works. So here you're measuring if it's if it's zero, you're not gonna apply those operations, but still, well, here you're just trashing them.